Okay, so it is recording now. Okay. And so I think what I wanted to start with is I'm going to skip some like the vector stuff, and I want to start with linear systems of equations, and I want to try to work through LU decomposition through this review. And then if I have the time, I might cover some of this earlier stuff, okay? But let's go to linear systems of equations first. If you guys have a question at any time, feel free to ask it. Whoops. Okay. So if you post in the chat, I am monitoring it on another monitor. And you can also unmute yourself if you have a mic and speak to it as well, okay? All right. Okay, so to start off talking about linear systems of equations, here I have a pretty simple example. So this is a system with 2 equations and 2 unknowns. And let's just say if we wanted to solve this equation, most of you I think already know how to solve it. Okay. So one thing that we could do is we could start by multiplying both sides of the first equation by 2. So I'm going to do that real quick. So it gives us 2x minus 2y is 10. And after doing that, we can now subtract these equations from each other. If we do that, the x's are going to cancel out. We're going to get negative 2y minus 3y is negative 5y equals 10 minus 0, so 10. And therefore, you get y is negative 2. From there, we can take this and plug it into any of these other equations that we have. Okay. And so let's say I plug it into the first equation. So you get x minus y, where y is negative 2, is equal to 5. So add negative 2 over, and you'll get that x is equal to 3. And that gives us the solution to our system of equations, okay? All right. So of course, for a larger system, it's a little bit more difficult to solve, but you guys have learned a certain like algorithm for how to solve those systems of equations, where you do elimination plus back substitution. And I'm going to do a couple of examples of that, but before I get to it, I want to just like go over a couple other things related to linear systems of equations first. I thought it was maybe worth going over the row picture and the column picture for a moment. So I'm going to use this linear system of equations as an example of that, okay? And let's see here. Okay. So if you guys, great question. So I will get to that when I get to LU factorization. In a sense, there really is not that much difference, as you'll see though, okay? So what's the difference? There isn't that much of a difference is what I was saying. All right. So if you guys remember what the row picture was, the row picture is you have 2 equations here, and those 2 equations, each of them represents the equation of a line. So the row picture is graphing the 2 lines, and where the 2 lines intersect, that would be the solution to the system of equations, okay? So let me try to draw the row picture real quick. So what I want to do is graph each of the equations. So let's start with x minus y equals 5. Okay, so x minus y equals 5. If you rearrange it, it's y is x minus 5. Okay. So that's going to give us a y-intercept of -5 and a slope of 1. Okay. So here is the first line, y equals x is minus 5. Next, I also want to graph the line 2x plus 3y is 0. Okay, so that's the same as y is -2 over 3x. So the y-intercept is 0, and the slope is -2/3. So if I go down 2, sorry, go over 2, go down 3. Okay. That's not very straight, but that would be the second line. And let's see here, did I draw the picture very well? Let's see here, the solution was supposed to be 3, -2. So, oh, I see, I did the slope backwards, didn't I? All right. Yeah, it should be rise over run. I did run over rise. Okay. So yeah, so if x goes over 3, wait, no, rise over run. So I go down 2, and then I go over 3. There you go. All right. Go down 2, go over 3, and now I'll draw my line. There you go. Okay. So then where the two lines intersect, here you can see that they are intersecting when x is 3 and when y is -2. And that is exactly the solution that we found earlier. Okay. So then that's the idea of the row picture, just showing where the two lines intersect. And that would be the row picture, okay? And then there was also the column picture as well, so I do want to talk about that one. Between the row picture and the column picture, if I had to pick one being more important than the other, I think you could make the case in this class that actually the column picture is going to be more important, okay? Yeah, the recording will be uploaded to YouTube. So I'll probably be able to do it later tonight, or at the latest, I'll do it sometime tomorrow morning as well, okay? All right. So yeah, I also want to illustrate what the column picture is. So let me try to draw the column picture for this example. All right, so what was the idea of the column picture? So let me take the system of equations that we had again. Okay, so we can rewrite this system of equations as like a vector equation. So we can rewrite it as like x times the vector 1, 2. So 1, 2 coming from the coefficients, plus y times the vector -1, 3, equals 5 and 0, okay? And again, we saw the solution earlier, x equals 3 and y equals -2. So what we want to do for the column picture is we want to illustrate how 3 times this first vector, the first column, plus -2 times the second column, we want to illustrate how that's going to be equal to 5, 0. See here, Taco Bell. All right, how do you find the YouTube recording? So if you go to YouTube and just search like a UT Dallas peer tutoring, that's probably going to take you to our webpage, and that's where I'm going to upload the recording later. Okay. Yeah, perfect. Oh yeah, and I will email everyone once I've uploaded it. So I'll send you guys the link as well. All right. Okay, so here's how the column picture works. So let me draw my axes again. Let's see here, it might be better to start lower. Okay, so what I'm gonna do in the column picture is I'm gonna start by drawing the vectors 1, 2, and -1, 3. Okay, so first vector 1, 2, it's gonna be out to there, okay? So that's 1, 2. Next, let me draw vector -1 and 3. So -1 and 3. Goes up to here, okay? Okay, so next in the column picture, what you want to do is you want to use the solution that you found for this next part. So we found that x is equal to 3, so what I'm going to do in my picture is I'm going to multiply 1, 2 by 3. Okay. So then that takes me all the way out to here. So this is 3 times the vector 1, 2 now. And then similarly, we found earlier that y was -2. So what I want to do is take the vector -1, 3 and multiply it by -2. So since we're multiplying by negative, it's going to go in the opposite direction. And then the 2 means that you're going to double the length as well. So this vector here should be -2 times the vector -1 and 3, okay? Now it should be that when we add these two vectors, okay, that their sum should be equal to 5, 0. Okay? So here's 5, 0, okay. So remember that visually to add two vectors, when your vectors are connected tail to tail, that their sum is supposed to be the diagonal of the parallelogram that they form. So if we were to form a parallelogram now with these two vectors, you can kind of cheat a little bit just to make sure that your picture looks decent. And then this vector here, the sum of the diagonal of that parallelogram, that would be the sum of the two vectors, and you can see that it is equal to 5, 0, okay? So this is what the column picture looks like. This is showing how this particular linear combination of the two columns will be equal to the vector on the right-hand side of your equation, okay? All right, so there's different insights that you can gain from looking at the row picture and the column picture, okay? For the column picture, the main insight that we kind of get from it is that in order for the system of equations to have a solution, this vector that was on the right-hand side, you can kind of see it has to be a linear combination of the column vectors on the left in order for there to be a solution. So that's kind of the main insight that we get from the column picture, okay? So maybe I'll do like RHS for the right-hand side. So only if the right-hand side is a linear combination of the columns on the left-hand side. Okay. As for what kind of insights do you get by considering the row picture of a system of equations? The row picture gives us some sense for what are the possibilities regarding the solution to a linear system of equations. So here in this example, this is a case where we have a unique solution. And in the picture, that's reflected by the fact that the two lines are intersecting at a single point. And where they intersect, that's our unique solution, okay? But there are two other possibilities as well that one could encounter. So aside from having a unique solution, you could also have infinitely many solutions. That's another possibility. So this would occur, for instance, when you have two equations which are the same. So for example, if I consider the equation x minus y equals 2, and then 2x minus 2y is 4. Okay, so if you guys will notice, the second equation is actually just the first equation, but multiplied by 2. It's interesting, okay. So then because the second equation is just the first equation multiplied by 2, that means really these two equations are going to graph the same line. Okay. So what's kind of happening is this. If you were to draw the first line, it's y equals x minus 2. So the first line would look something like that. Y-intercept is -2, slope is +1. But the second line is the same as the first line because it's the same equation. So the solutions are supposed to be where the two lines intersect each other. In this case, the two lines are intersecting at infinitely many points. And so therefore, you're getting infinitely many solutions here, okay? The third possibility is that you could also have no solution to a linear system of equations. So an example of when you would have no solution, let's say we have the equation maybe like x plus y equals 1. And then, for instance, x plus y equals 2. So in this case, it is not possible to find an x and a y that satisfies both the first equation and the second equation, because it's not possible for 1 to be equal to 2. And visually, if you were to look at the row picture, what's going to happen here is you're going to get two parallel lines. So the first line, y equals 1 minus x, it's going to look like this. Okay. Whereas the second line is y equals 2 minus x, so it's just kind of shifted up 1 unit. And because the two lines are parallel to each other, they never intersect. And so that gives you no solution in that case, okay? And here we were only looking at a 2x2 system, so 2 equations and 2 unknowns. But it turns out that this will hold for any number of equations with any number of unknowns, that there's only going to be 3 possibilities regarding the nature of the solution. You could either have a unique solution, or infinitely many solutions, or no solution. And those are the only 3 possibilities, okay? So this is kind of the insight that one gets by looking at the row picture. Okay. Now, I want to talk about like doing elimination and back substitution. So this is how you're going to solve a larger linear system of equations with more equations and more unknowns. And I'm going to try and do 3 examples right now. So one example with a unique solution, one example with infinitely many solutions, and one example with no solution. So you guys can kind of see the difference between the 3 of them, okay? Okay, so to do elimination, so remember that there's like 3 types of what they call elementary row operations that you can perform. Okay. So the first type of elementary row operation, the one that you kind of do the most of, is adding a multiple of a row to another row. So this operation is analogous to the operation that we did up here, where we multiplied the first equation by 2, and then we kind of like subtracted it from the second row, or the second equation. That's the idea of this first type of row operation. The second type of elementary row operation that you can perform is you can also multiply a row by a non-zero number. And so multiplying a row by a non-zero number, that just corresponds to multiplying an equation on both sides by a non-zero number, okay? So for instance, how we took the first equation and multiplied it on both sides by 2, that would be equivalent to multiplying one of the rows by a non-zero number, okay? The third type of elementary row operation is swapping 2 rows, and that's just the idea that changing the order of your equations has no effect on the solutions, okay? Yeah, is there a question? Okay, all right. I think that was just maybe an accident. All right, so those are the 3 types of elementary row operations that you perform, and you use those in order to do the elimination plus back substitution procedure, okay? Now, the way that elimination and back substitution works is you want to perform elementary row operations to get your matrix into an upper triangular form. Once you get it into upper triangular form, then that's when you do your back substitution, okay? So I'm going to illustrate that with a couple of examples. And here I've got one example already set up. Okay. So what you want to do is you want to take this first number and you want to use this number as a pivot and eliminate everything underneath it. So I want to eliminate the -2 and the 3 in that first column right now. So to do that, we can take the second row and we're going to add 2 times row 1 to row 2. And to eliminate the 3 in the third row, we can take row 3 and minus 3 times row 1. Okay. So that's going to produce zeros in the first column now. And then we have to work out what the rest of the new system of equations is going to be. So if we continue performing the rest of the row operations, row 2 plus 2 row 1, this is going to be 2. This is 1 plus 2 is 3. 6 plus 2 is 8. Okay. Here we're going to get 4 minus 0 is 4. -2 minus 3 is -5. And then -3 minus 3 is -6. All right. Okay, so next we have a new pivot in the second column now. So that's our next pivot, and we want to use that to eliminate everything that's underneath it. So in this case, we just want to eliminate that 4 now in the second column. So to eliminate the 4, we can multiply the second row by -2, and then add that to the third row. So row 3 minus 2, row 2. So that's going to put our matrix into this upper triangular form now. So upper triangular just means that you have zeros beneath the main diagonal there, okay? Okay, let's finish the rest of the row operation. So we did row 3 minus 2, row 2. It's -5 minus 6 is -11. And then here, this is, what is that? -6 minus 16 is -22. So now that we've reduced the matrix to the upper triangular form, this is where we would stop and start doing the back substitution, okay? So we're going to convert this back into like a system of equations. So from the first row, we have 1x plus 0y plus 1z is equal to 1. The second row gives us the equation 2y plus 3z is 8. And then in that third equation, we have -11z equals -22. Okay. So here the idea is you see that in the last equation, we can immediately solve for z. So we're going to get z is equal to 2. And then we can substitute this back into the second equation now. So we plug in 2 for z. We now see that we can solve for y from this. So you're going to get 2y equals 2. So y is going to be equal to 1. Oh. Then now that we solved for y and z, we can substitute those back into the first equation now. So in the first equation, there's no y in the first equation, but we can plug in the 2 for z, and then we can solve for x, okay? So here you get x is -1, and then this would have been the solution to our system of equations that we had, okay? So I guess the reason why they call it back substitution is because you're starting with the last equation, you're solving it, and then you're substituting what you found back into the previous equations, and that's what backward substitution is, okay? So this was an example where we got a unique solution. So I do also want to look at examples where we're going to have infinitely many solutions and then where we have no solution. I know you guys haven't done too much of that so far this semester, but you've had like a few questions involving getting infinitely many solutions or no solution. And like after the first exam, you're going to be dealing a lot more with those cases of having infinitely many solutions or no solution as well, okay? Okay, so here's another system of equations. Here I just wrote it in this like augmented matrix form, okay? All right, so let's say we want to try doing elimination plus back substitution on this system here. So right now we have a 2 in this like pivot position. And it's a little bit inconvenient to use the 2 to eliminate the ones underneath it, because that's going to introduce some fractions into the problem if we were to do that. So instead of using the 2 as a pivot, if I'm just trying to solve the system of equations, what I would personally prefer to do is swap 2 of the rows right now, so I can get a 1 into the pivot position. 1 is like the easiest number to use as a pivot, okay? So I could swap row 2 with row 1 or row 3 with row 1. It doesn't really matter. Maybe I'll take row 1 and row 3 and swap them. Okay. So that puts a 1 in the pivot position up top. And that's just going to make doing the math a little bit easier now. Okay. So now here's our first pivot, and we're going to use it to eliminate everything underneath it. So we would do row 2 minus row 1, and row 3 minus 2 of row 1. Okay. All right. And then if we work out the rest of the matrix here, we have row 2 minus row 1, that's going to be -1 plus 3 is 2. This would be 1 minus 0. This is a 0 minus a -1, so it's going to be +1. We're also going to have 0 plus 6, so this is going to be 6 here. It's going to be 3 minus 0 is 3. And then that's 1 plus 2 is 3. Okay. If you guys have any questions about what I'm doing, just let me know at any time. Also, I'm not perfect, so I know that I occasionally will make mistakes. So if you see me like make a mistake, let me know that as well, okay? Also, give me 1 minute. I'm going to try and do something with my computer real quick. Let's see here. What did that right? No. Okay, that's fine. So can we also do negative row 2 plus row 1? So to solve a system of equations, those are okay to do. However, I would be a little bit cautious about doing things like that when you're doing like the LU decomposition. Those will actually not be allowed if you're trying to do the LU decomposition. And we can maybe talk more about that when I get to it, okay? But when you're just solving a system of equations, then those types of operations are valid, okay? But be wary, there are maybe some situations where you want to do it the particular way that I'm doing it now, instead of doing it like that. Is that good? Okay, all right. Okay, so from here, we're trying to get it into the upper triangular form. So the next thing that we would do is we would take our next pivot, which is this 2 here, and we're going to eliminate the 6, which is underneath it. So to do that, we would take row 3 and we would subtract 3 of row 2 from it, okay? And here, what you guys will notice is when you do this row operation, it gets us this row of zeros here, okay? Okay, so here we ended up with row 0. So this is, I don't know if this is really important, but I know your textbook calls this a permanent breakdown. A temporary breakdown is when you get a 0 in the pivot position, but you can swap rows to remove that problem. But if you get a row 0, that's a permanent breakdown, because no matter how you try to swap the rows, you always have that row of zeros there. So you're always going to have a 0 in the pivot position, okay? So when you have a permanent breakdown, that's an indication that you will either have infinitely many solutions or you'll have no solution, okay? Yeah, okay, yeah. So if you have a situation like that where it's 0, 0, 0, but then the right-hand side is not 0, that's an indication that you have no solution, right? Okay. And I do have an example of that coming up as well. But yeah, that would mean that there's no solution. In this case, what's going on in this example is we are actually going to have infinitely many solutions. So let's kind of see how this works, okay? So in the first row, if I convert that into an equation, it's x minus 3y plus 0z is negative 1. The second row gives us the equation 2y plus 1z is 1. And then the third row is 0x plus 0y plus 0z equals 0. So you don't have to write that equation down, okay? So really, we sort of really only had 2 equations here, but we had 3 unknowns, okay? So what's happening here is since we have only 2 equations, we're actually only going to be able to solve for 2 of our variables, okay? So what I'm going to do is I'm going to take the second equation and I'm going to just move things around in the second equation. I'm going to solve for y. So I'm going to move the z over and then divide by 2. So we're going to get y is 1 minus z over 2, okay? All right, so then if I do that, I can do back substitution. I can substitute this into the first equation. So we'll get x minus 3, and then we're going to replace y with all of this. And from here, we'd be able to solve for x now. So to solve for x, we would just move everything over. And you'll get x is negative 1 plus 3 over 2 times 1 minus z. Let's write it like that. Okay. So there we solved for x and y. So now there's a question of what's going on with z, okay? So z is an example of what we call a free variable right now, okay? So the idea of a free variable, here there's no restriction on what z can be. So z is actually free to be any number, and that's kind of why we're calling it a free variable. And there's a couple of slightly different ways that people will do this next part, but the way that I just personally like to do it myself, since z is a free variable, what I'm going to do is I'm going to assign to z a parameter, so basically another variable. I tend to use like r, s, and t for my parameters, but you can use like any other letter other than x, y, z, since we're already using those in the problem, okay? All right, so I'm going to just assign z equal to some variable t. So t can be any real number. And then if z is equal to t, I can replace or substitute that into these 2 equations. So that's going to give us y is 1 minus t over 2. And likewise, we plug in t for z, you're going to get x is -1 plus 3/2 times 1 minus t. So then here, this represents a set of infinitely many solutions to our system of equations. You're going to get one solution for each possible value of t. And since t can be any real number, and there are infinitely many of those, so that's why we have infinitely many solutions here, okay? So when you have infinitely many solutions, this is like one way that you could represent your solutions. All right, now someone made a good observation, which is that you don't have to choose z to be a free variable. So it would have been possible to choose x to be a free variable as well, as someone is asking about. And here it's also should be possible to choose y as a free variable as well. Okay. So you have some freedom as to which variable you choose to be your free variable. Okay. Now later on in this class, as I was saying, you are going to be dealing a lot more with the situation of infinitely many solutions. You're probably going to see that more than the other two cases, I would say, for the rest of the semester after this first exam. I will say that there is sort of a convention that is useful to follow and some of the things that you're going to be doing later. So I'll just go ahead and mention what this convention is, just like as a heads up for the future. So again, you don't have to do it this way though, but sometimes it's useful to follow this particular convention, which is, so this is a convention on which variable should you choose to be your free variable, okay? So this convention is that the free variables should correspond to the columns without a pivot. This will be useful in some of the things that we're going to do later, okay, in this class. But this is actually kind of why I ended up choosing z to be the free variable, because in our reduced matrix, it's the third column that's missing a pivot. So according to this convention, if the third column is missing a pivot, I want to choose the third variable, z, to be the free variable, okay? But as you can see, and as we kind of talked about just now, you don't have to follow that convention, but it's going to help with some of the things that we'll do later in the class. All right. All right, so maybe I'll pause for a moment and just ask if there are any other questions about this example or just getting infinitely many solutions in general. Okay. I'll also maybe say one more thing that just kind of popped into my head, which is this convention, one of the things that it kind of highlights actually is that it kind of tells you when you're going to have infinitely many solutions. So basically, you're going to get infinitely many solutions whenever you have a free variable, okay? And so with this convention, there's a correspondence between free variables and columns without pivots. So therefore, we can actually say that you're going to have infinitely many solutions precisely when you have a column that's missing a pivot. So that's kind of what you'd want to look out for as you're doing like elimination on a matrix to know if you're going to have infinitely many solutions. If you see a column that's missing a pivot, that's kind of the main giveaway, okay? And then just real quick, and then I'll move on to something else next. Let's just look at one more example here. So if we try to do elimination on this, so we'd start by doing row 2 minus 2 row 1. Okay, so if we do these operations, 3 minus 4 is -1. This is 0 plus 2. Okay. And then let's say we did row 3 plus row 2 next to get to the upper triangular form. So if you go through the process of elimination, you're going to end up with this situation, which we kind of just talked about. Oh, did I mess up? Oh yeah, thank you. Yeah, row 3 minus 2 row 1. Yeah. All right, perfect. Thank you. So when you get to a situation like this, where you have a row of zeros, but then the right-hand side is not 0, this is like the indication that you have no solution, okay? Just because you can see already in that equation there is no xyz that will satisfy that equation, so there's going to be no solution, all right? So then just to sort of summarize, the no solution is when you have like 0 equal to something not 0. Okay? And then the infinitely many solution case will happen when you have a column that's missing a pivot, all right? Okay. So let me see what I have next. Okay. So I want to spend some time talking about matrix multiplication next. Hopefully you guys are pretty familiar with it, but I'll go over it a little, okay? So if we have two matrices, A and B, so if A is a size M by K matrix, and that means that it has M rows and K columns. Okay, that's what the notation means. And then we have another matrix B, which is size K by N. Okay. All right. So it's these numbers that have to match in order to multiply the two matrices together. Okay. So the number of columns in A would have to be the number of rows in B in order to calculate A times B. Okay. If those sizes are not matching up, then that means the product will not be defined. Okay. And then if it is possible to multiply A and B together, then it's these like outer numbers, the M and the N, that tell you what the size of the result is going to be. So here, A is M by K, B is K by N. The size is of the product is M by N. Okay. So sometimes it is useful just to think about what the sizes of your matrices are and what the size of the product is going to be. So that's how you do that. As for how you actually multiply the matrices together, here I've written down like 3 different rules for thinking about how to multiply two matrices together. The first rule that I've written down, this is the one that you'll be using the most of for computation purposes, where it computes the product entry by entry, okay? And this says that the entry in the ith row in the jth column of AB will be equal to the ith row of A and it's a dot product with the jth column of B. The second kind of method that I wrote down for multiplying two matrices, this calculates each row of the product. So it says that the ith row of AB, it's actually equal to the ith row of A multiplied with the matrix B, okay? Lastly, this third one looks at the columns of the product. Okay, so the jth column in the product AB is going to be equal to A times the jth column of B. Okay. So let me do some examples, just kind of illustrating how this works. Just a few examples, not too, won't take too long. So let me create just a couple of matrices with some numbers in them. So let's make A like a 3x2 matrix to start with. So let's do 1, -2, 3, 1, 0, 2. Let's take another matrix, we'll call it B. Let's say B is going to be 2x3. Let's do 1, 0, 2, 3, -1, 0. Okay. So if I want to multiply A times B, okay. Okay. All right, so first, because these numbers match up, that means that the product is defined. Okay, so that's good. And then because, oh, so now that those are defined, then these two numbers tell us what the size of the product will be, okay? So when we multiply A times B, the result is going to be a 3x3 matrix. Okay. So let's see how that is going to work. So I'm going to calculate A times B just using this first property here, okay? Oh, there you go, okay. All right. So what I want to do is I want to take each row of A and multiply it to each column of B. And when I do this, we're going to be doing like dot products, okay? Okay, so the first row of A times this first column of B, the dot product would be 1 times 1 plus -2 times 3. I won't write all of them out, but let me just write the first couple of them out. So 1 times 1 plus -2 times 3. And then if we take the first row of A times this second column of B, that's going to get us the next entry. So it'll be 1 times 0 plus -2 times -1. So 0 plus 2 is what that's going to be. Then if we continue taking the first row of A times this last column of B now, okay, doing the dot product, it's going to be 1 times 2 plus -2 times 0. Okay. So right now that fills out like the first row of the product. Okay. And then just kind of quickly doing the rest of it. So if you take the second row of A, and now you want to do the dot product with each of the columns of B. Okay. So next we're going to get 3 times 1 plus 1 times 3. That's going to be 6. 3 times 0 plus 1 times -1 is -1. Okay. And then lastly, you're going to get 3 times 2 plus 1 times 0. That's going to be 6. All right, and let me know if you guys like aren't following along. Okay. So then lastly, you're going to take the last row of A times each of the columns within B. Okay. So we're going to take like 0 times 1 plus 2 times 3. So that's going to give us another 6. There's a lot of 6s here. Next, we'll do 0 times 0 plus 2 times -1. That's -2. And lastly, we'll take 0 times 2 plus 2 times 0, that gets us 0, okay? So it's a little bit awkward at first when you're like first learning matrix multiplication, but if you just like do just a couple of examples, you'll probably get the hang of it pretty quickly, okay? Any questions about that? Okay. I also want to comment on these other two rules for matrix multiplication that I wrote down. Okay. So let's look at the second rule right now, that the ith row of the product is taking the ith row of A and multiplying it with B. That's kind of what we ended up doing to complete like the first row, right? So remember that to calculate this first row, we took the first row of A and we had to multiply it to each column of B, doing like 3 different dot products. So that's essentially just taking the first row of A and multiplying it to all of B, and that filled out the first row in the product, okay? And then likewise, just looking at this last rule. So say if we were focusing on the first column in the product here, okay? To calculate just the first row of the product, what you can do is take matrix A and multiply it with just the first column of B, okay? So if you did that, you would get like 1 times 1 plus negative 2 times 3. That's the negative 5 here. If we take 3 times 1 plus 1 times 3, that gets us the 6 that's over here. And then lastly, 0 times 1 plus 2 times 3 gives us the 6 at the end, okay? So A times just that first column in B gave us the first column in the product, okay? All right. So if there are no questions about matrix multiplication, then I don't want to spend too much time on it. One more quick comment then is just some properties of matrix multiplication. So matrix multiplication is associative and it's distributive, okay? But note in general that AB is not equal to BA. So whereas that is true for numbers, that is not true in general for matrices, okay? All right. So moving along, I want to talk a little bit about elementary matrices next. So an elementary matrix is any matrix that can be obtained by performing one elementary row operation on an identity matrix, okay? So here I just have some examples. So here we have the 3 by 3 identity matrix. So remember the identity matrix, it just has ones in the diagonal and zeros everywhere else. And also maybe I should make a quick comment on what's special about the identity matrix, right? So let me talk about that real quick. So people usually use I for the identity matrix. Okay. This is a 3 by 3 identity, so some people might do like a subscript of 3 to represent the size, but yeah, typically people use I for the identity. The main important property of the identity matrix is that A times I will be equal to I times A, and both of those are going to be equal to A, okay? So this is kind of similar to how like taking a number A and multiplying it with the number 1. just leaves you with the number A again. So the identity matrix is kind of like the matrix analog of the number 1, okay? Okay, so that is important to know about the identity matrix. Okay. So what I did here is I took this identity matrix and I just performed 3 random elementary row operations on it, okay? I did like 1 of each type. So if you do one of these like elimination type of row operations where you add a multiple row to another row, so that will leave you with an elementary matrix here, which I'm just calling E1. Another type of elementary row operation is swapping 2 rows. So if you swap 2 rows of the identity matrix, the result is going to be another elementary matrix. And lastly, the third type of elementary row operation that we had was multiplying a row by a non-zero number. So if we perform that type of operation on the identity matrix, it gets us another elementary matrix, okay? Okay, so then just to kind of keep in mind again, so an elementary matrix, it's a matrix that can be obtained by performing 1 elementary row operation on an identity matrix, okay? And as for what is special about elementary matrices, I'll kind of illustrate that here real quick. So multiplying a matrix on the left by an elementary matrix has the effect of performing the corresponding row operation. And I'm going to do a little computation here just to illustrate what I mean by that. So this is the elementary matrix E1 from here, which we obtained by doing this particular row operation on the identity, okay? So if we do the matrix multiplication, doing the rows dot product with each of the columns, the first row, you're going to get 100 dot product ADG. That's going to be A plus 0 plus 0. Next, you'll get like B plus 0 plus 0, C, okay? The second row is a little bit different. So if you do the multiplications, it's the second row dot product with each column, you'll get 0 plus D minus 3G. Okay. Next, you'll get 0 plus E minus 3H. And then you'll get 0 plus F minus 3I. Okay. In the third row, to get that third row, take the third row of E1, multiply it to each column doing the dot product, and you're going to get GHI. Okay. So then notice that from the original matrix here to the product that we had, you can obtain the product from the original matrix by doing row 2 minus 3 of row 3, right? So row 2 minus 3 of row 3 will leave you with this for the new row 2. And you'll notice that this row operation is the same row operation that we did to get the elementary matrix E1 in the first place, okay? So when you multiply a matrix on the left by an elementary matrix, the result is the same as if you just performed the corresponding row operation on that matrix, okay? The same is going to be true if you used E2 or E3. So for example, if you did E2, and I'm not going to like work this out, just kind of real quick though. E2, if you multiplied that with this matrix A, what you would find is that the product is simply A, but with rows 2 and 3 swapped. Okay, and row 2 swapping with row 3, that was the elementary row operation that corresponded to the elementary matrix E2. Okay, so the product would just have been A, but with rows 2 and 3 swapped. And then just real quickly then, so if you took E3, the last elementary matrix that we have like up here, you guys can check if you take E3 and you multiply it with this matrix A again, the product, the result, is just going to be matrix A, but with the first row multiplied by 2. Okay. And multiplying row 1 by 2, that was the elementary row operation that corresponded to the elementary matrix E3. Okay. So I'll be doing some stuff with elementary matrices and some of the other problems and examples in this review. But for now, this is just what elementary matrices are and why they are special, okay? Any questions about that? Okay. So let's talk about matrix inverse now, all right? So I think that's one of the most recent topics that you guys have gone over. So the notion of a matrix inverse, it only applies to square matrices. So your matrices have to be like size n by n in order to have an inverse. And so if you have two matrices A, B, which are size n by n, A and B are going to be inverses of each other if their product is equal to the identity matrix, okay? In that case, A is going to be the inverse of B, and likewise, B is going to be the inverse of A. If you guys remember how the identity matrix was like the matrix version of the number 1, then you can kind of see what's going on in terms of the notation. So we're saying A times A inverse is equal to the identity matrix. Likewise, A inverse times I is also going to give you an identity matrix as well, okay? So that's similar to how taking a number A multiplied by A to the negative 1 would give you the number 1, okay? So it's like analogous to that idea with numbers, okay? So I'll talk about how to calculate matrix inverses shortly. But there's a few like special cases which are kind of worth keeping in mind, I think. So for the special case of a 2 by 2 matrix, we have this formula for what the inverse of a 2 by 2 matrix is, okay? So in general, it's not easy to calculate the inverse of a matrix, but 2 by 2 matrices are small enough that you can just memorize that formula for them. And maybe just a quick example to like apply that formula. So let's say if we had the matrix 1, -2, 3, -4. So to calculate the inverse of this matrix, so we would do 1 over, okay, so A times D is 1 times -4, minus B times C is -2 times 3, which is -6, okay? All right, so then in the formula, what you want to do is the diagonal entries will get swapped, okay? So instead of 1, -4, we're going to swap them. So it's going to be -4 and then 1 on the diagonal. For the off-diagonal entries, you want to put a negative sign in front of them. So instead of -2, here in the inverse, it's going to be negative, -2 is +2, and this is going to be -3, okay? So it looks like it's 1/2 times this matrix. Okay. All right, so then that would be the inverse of this 2x2 matrix here, okay? And if AD minus BC, if that turns out to be equal to 0, the 2 should be positive. Yes, thank you. Okay. And then if AD minus BC is 0, then you're going to be dividing by 0 in the formula, which means it's no good. So what's happening is if AD minus BC is 0, that means that the matrix is not invertible. Okay? So not every square matrix is going to be invertible, meaning not every square matrix will have an inverse. And so for 2x2, you have the simple criterion to check if it's invertible or not, okay? I think it's also useful to talk about the inverses of elementary matrices. They're really simple. So here I have the 3 elementary matrices E1, E2, and E3 that we kind of were using earlier. And I've also kind of written what their inverses are, okay? So notice that for E1, its inverse is the same thing, except you change the sign of this off-diagonal entry. So -3 becomes +3. That's the inverse of E1. For E2, here I have that the inverse of E2 is itself. And for E3, you can see what happened for its inverse. We took the 2 on the diagonal and we just did its reciprocal. So 1/2, okay? So quick reasoning for why this is the case. So remember that each of these elementary matrices corresponds to an elementary row operation. Okay. So the elementary row operation corresponding to E1 was doing row 2 minus 3 row 3. So if you do that operation on the identity matrix, it gives you E1, okay? That's what we did earlier. So every row operation has an inverse row operation, meaning that you can undo any row operation with another row operation, okay? So if you subtract 3 of row 3 from row 2, you can undo that by adding 3 of row 2 back to row 2. So row 2 plus 3, row 3, that's like the inverse row operation to row 2 minus 3, row 3. And then the elementary matrix that corresponds to this row operation, that's this guy here. So it's just, you end up getting a 3 in this 2, 3 position of the matrix, okay? And so the elementary matrix that corresponds to the inverse row operation will be the inverse of the original elementary matrix, okay? So similar for the other two, so real quick, E2 corresponds to swapping rows 2 and 3. How do you undo that? You just swap row 2 and row 3 again. So that's why the inverse of E2 is itself. Because to undo the row swap, you just do the same row swap again, okay? Lastly, E3, this elementary matrix, it corresponded to multiplying the first row by 2. How do you undo that? You multiply the first row by 1/2, okay? And then this would be the elementary matrix corresponding to this row operation, okay? And so then this would be the inverse of E3. So it's pretty simple. For these elementary matrices where you have a number, a single non-zero number off the diagonal, change the sign and that's the inverse. If the number is on the diagonal, you do the reciprocal rather than changing the sign. If it's a row swap, the inverse is itself, okay? All right. And then in general, to find the inverse of any matrix, there is a procedure for doing that. So the way it works is you take your matrix A and you augment it with an identity matrix. And then you perform row operations until you reduce A to the identity matrix. And then whatever you have remaining on the right-hand side, that is going to be the inverse of A, okay? I'm going to illustrate that with this example down below. But real quick, if it is not possible to reduce A to an identity matrix, then this procedure is going to fail, okay? So when that happens, that just means that your matrix A is not invertible, okay? So for now, this is the main way of checking whether a matrix is going to be invertible or not. You just want to see if you can reduce it to an identity matrix. Okay. So let me try to illustrate finding the inverse with this example here. There's also a couple other things that I want to do with this example as well, right? But let's just start with part A, which is finding the inverse. So the way that you do that for larger matrices, you're going to augment them with an identity matrix. So that's what I'm doing right now. Okay. Now we're just going to do a bunch of row operations. We need to get the left side reduced to an identity matrix. So to do that, I'm going to start by swapping rows 1 and 3, okay? Because that's going to give us a pivot, or 1 as a pivot in this position, which is going to be easier to use for the elimination. Now be sure that you apply these row operations to the right-hand side as well. So I also need to swap rows 1 and 3 over here. Okay. Now we're just going to start doing the usual elimination process. So here we're going to do row 2 plus row 1 and row 5 minus 5 row 1, okay? That will give us 1, 0, 0 to start with. Now continuing to add row 1 to row 2. So we're going to get -3 2. And then on the other side, adding them 0, 1, 1. This is row 3 minus 5, row 1. So that's going to be 2 plus 5 is 7. 0 minus 5 is negative 5. 1 minus 0 is 1. This will be 0, and this will be negative 5. Okay? Okay. Okay. So then next, this negative 3 will kind of be like the next pivot. So we'd have to use it to eliminate the negative 1 and the 7 that's above and below it. Okay. Now, right now, if we do the elimination, we are going to get some fractions. So personally, I try to avoid fractions as long as possible when I'm doing these problems. Okay. Now, if the inverse is supposed to have inverses in it, then at some point you have to get inverses. Oh, sorry, you have to start getting fractions in your work. So you can't put out the fractions forever if the answer has fractions in it, okay? But sometimes I try to do something like this to avoid fractions, all right? So I'll kind of show you guys just like something that I will sometimes do. To avoid fractions, I would like to have a 1 as a pivot, okay? So I might do a row operation to get a 1 in the second column first. And then once I have that 1 in the second column, I'm going to swap it and use it as a pivot, okay? So what I'll do here then is I'm going to take row 3 and I'm going to add 2 of row 2, okay? Let me continue down here now, okay? Yeah, so that's another method of finding the determinant of a matrix, or sorry, finding the inverse of a matrix. However, that's not going to be covered until after exam 2 in this class, which is why I'm not going to teach it to you guys. But if you know it already because you learned it from somewhere else, then yes, I don't see why you couldn't use that other method. And my sense is your professors would give you credit if you used that method. But as I said, though, I'm not going to go over it because you guys will actually cover it after the second exam in this class. Is there a more efficient way for finding the inverse of a matrix? The answer is no. So you're kind of out of luck for that, okay? All right. Where was I? Okay, so I was going to do row 3 plus 2 row 2 here. So the purpose of this row operation was to get a 1 as a pivot, okay? So if we add 2 of row 2 to row 3, the new row 3 will be 1 minus 1. This is still a 1. This would be a 2, and this would be a negative 3, okay? All right, and then from there you can do row 2, swap with row 3. So that's what I would like to do next. Okay. And so now that we have a 1 in that pivot position, it's going to be easier to do the elimination, and we can stay about the fractions at least for a little bit longer, okay? So I'm going to use that 1 as a pivot, and here I want to reduce all the way to an identity matrix, not just up a triangular form. So that means I would not only eliminate the -3 that's underneath this pivot, I would also eliminate the -1 that is above it as well, okay? So which means I would do row 1 plus row 2 here, and row 3 plus 3 row 2, okay? So then we're pretty close to completing the identity on the left. So there's going to be one more column that we have to work with afterwards, okay? Okay, so let's see what we get here. If we add row 2 to row 1, you're going to get 0, 1, 2, and -2. Okay, that's convenient. And then down below, we're going to get row 3 plus 3 row 2. That'll be 2 minus 3, -1. 0 plus 3. Okay. 1 plus 6 is 7. And then 1 minus 9 will be -8, okay? All right. And at this point, we'll just do a couple more things. So to get the identity matrix, we need this to be a +1. So what we can do there is just do -1 times row 3, okay? And then now we have this third pivot. And there's only one thing that we need to eliminate above it. So we're going to do row 2 plus row 3. And that will give us the identity matrix on the left, okay? So now this matrix that we have on the right-hand side is going to be the inverse of A. So if we add row 3 to row 2, that's -2, -5, -5. Okay. All right, so then here is a inverse, okay? Okay, so does anyone have any questions about that procedure? All right, go ahead and ask. How do you write it in terms of an equation? Sure. So we'll talk about that as well, okay? So this was intended to only be part A of this example. So I do want to illustrate a couple of things you can do with the inverse and also with elementary matrices. So every row operation that we did is going to give us an elementary matrix, okay? Which will come into play for parts C and D. I do want to take a look at part B real quick. So I just want to illustrate one of the applications of matrix inverse. So I'll look at B first and then, yeah, okay. And we'll get to all that when we talk about part C and D, okay? So just give me a second. I'm gonna do something with part B right now. I'm going to do that down below. Okay. Okay, so just real quick for this. One of the things that you can do with the inverse of a matrix is you can use it to solve a system of equations, okay? So here we have a system of equations, and I'm just going to write it in matrix form. So in the form like AX equals B. So here I'm taking the coefficients, multiplied with the vector of variables, x, y, z. And then on the right-hand side, we had 1, 2, 3. All right, so in order to get the solution to this equation, what we can do is if you multiply both sides of the equation on the left by the inverse matrix, okay? What happens is A inverse times A gives you the identity matrix. And we know that the identity is like the number 1, so I times x is just x, okay? So in other words, you can actually solve for x by simply multiplying A inverse with B, and that will get you the solution to the system of equations, all right? So since we calculated the inverse, that means you can use it to solve the system of equations. So the solution for x, y, z is going to be A inverse times B, which is 1, 2, and 3, okay? And then you would just finish the matrix vector multiplication to get the solution for x, y, z, all right? But I just wanted to illustrate that, yes, once you have the inverse, you could use it to solve a system of equations. But I'll leave it at there because I know you guys seem to really want to get to C and D. So I don't want to take up the time multiplying the numbers out. So let's talk about what's going on with C and D, okay? So all of the row operations that we performed have a corresponding elementary matrix. So for this first row operation where we did a row swap, we swapped row 1 and row 3. So if you swap row 1 and 3 of the identity matrix, that gets you the corresponding elementary matrix, okay? Okay. Now for the notation, I don't think it really matters, but if I were to give this a notation, I might do something like P13, okay? So when you have a matrix, which is obtained by swapping the rows of an identity matrix, those are usually called permutation matrices because they're just the identity but with the rows permuted, so like reordered. So if you want to give this matrix a name, you might use P because it's a permutation matrix, okay? All right. All right, so then we did a couple more. Well, okay, so now remember that when you multiply a matrix on the left by an elementary matrix, it gives you, or it has the effect of corresponding the, it has the effect of performing the corresponding row operation. So if we take this matrix P13 and we multiply it with A on the left, that's going to produce this matrix here, okay? So P13 times A is just A, but with rows 1 and 3 swapped. Okay. Next, we did 2 elimination type of row operations. So we did add row 1 to row 2. So the elementary matrix corresponding to that is going to be the identity matrix, but with a 1 in the 2-1 position. And you could obtain that by adding row 1 to row 2 of the identity matrix, okay? And then row 3 minus 5 row 1. That's going to give us another elementary matrix, which I know you guys usually call E31. And so this matrix is going to be the identity matrix, but it's going to have a -5 in the 3-1 position, okay? All right. So if we take this matrix, which was P13 times A, and then we're going to multiply it on the left by E21 and E31, okay? Multiplying these two on the left will produce this matrix, because multiplying by those two elementary matrices will just perform these two row operations, okay? So if I continue this process, so I'll try to do it a little bit more quickly now. Yeah, and the order for those two actually doesn't really matter because they were performed at the same time, okay? So let me try to do this a little bit more quickly now. So E32 will be the identity matrix, but with 2 in the 3-2 position. 3-2 position, okay. So let's call this one E32. And so this matrix that you have over here is going to be E32 times this, okay? Oh, okay, that didn't work. Okay. Okay. Yeah, so if we take E32 and then multiply it to everything else that we have so far, this product of matrices is equal to this matrix here right now, okay? So every time that you do a row operation, it's going to add another elementary matrix, and that elementary matrix, it always goes on the left right now, okay? This will give us another permutation matrix, P23. So swap rows 2 and 3 in the identity matrix, okay, to get P23. We get a couple more elementary matrices here. Then we just finish writing out the rest of them, and then I'll cut to the end, okay? So here we have like an E12. So we did row 1 plus 1 of row 2. That's going to add a 1 in the 1-2 position of the identity matrix. Yeah. This is going to give us another E32. So it's different from this one here, okay? So maybe I'll put a prime on it just to distinguish it from the other E32 that we found previously. Okay, but this one, we did row 3 plus 3 row 2. So that's going to be an identity matrix, but with a 3 in the 3-2 position. Okay. There's 2 more that we did. So -1 times row 3. Okay, so take the identity matrix and multiply the third row by -1. And that would be the corresponding elementary matrix, okay? And I don't really know what you guys might call it. Maybe I'll call this one E33, since this was affecting this 3-3 entry in particular, okay? And then lastly, this will give us a matrix E23. So we're adding 1 of row 3 to row 2. It's going to give us a 1 in the 2-3 position. All right. So at the end, if you take matrix A and you multiply on the left by all of these elementary matrices, the first one is the first one that multiplies with A. Next, we did these two. So those are the next two in line. Then we did this E32 next. Then we had P23 over here. And then next we had E31 and the E32 prime from these two row operations. Then we have the E12. Oh, wait a second. Did I mess up? Yeah, okay, I messed up. This one should be E12. Okay. So this E31 was for this actually. But row 1 plus row 2, that was E12, okay? So E12, and then this one here. Okay. And then there's 2 more. So we had the E33 from multiplying row 3 by -1, and finally this last row operation, which gives us the E23. So when you multiply all of these matrices together in that order, it has the effect of performing all the row operations that we did on A. And after performing all those row operations, we know that they reduced A to an identity matrix. So that gives us this equation here. So because we have a matrix here times A being equal to the identity matrix, that means that all of this product of elementary matrices must be A inverse, okay? So then that's how you would express the inverse of A as a product of elementary matrices, okay? So I'll pause real quick. Any questions about that? Okay. Now, there's another part to here, though, which was to express not A inverse as a product of elementary matrices, but to express A as a product of elementary matrices. So let's talk about how we would do that, okay? I'm going to do that off to the side here. So we have this factorization of A inverse as a product of elementary matrices. Okay. So to get A as a product of elementary matrices, A should just be the inverse of this product. Okay. So just like inverse both sides to get A, all right? Now there's a property of matrix inverse, which is when you apply the inverse to a product of matrices, you have to reverse the order of that product as you distribute the inverse to each term, okay? So what that means is to invert this product, I'm just going to apply an inverse to each of these matrices. But then I also need to write them in the reverse order. So P13 is going to go first on the left now, inverted. Then it's going to be E21 inverse and so forth, okay? And then the inverse of each of these elementary matrices is another elementary matrix. We kind of talked about that earlier. And we talked about how to get the inverse of elementary matrices as well. So for these elementary matrices, just change the sign of the off-diagonal entry. For the permutation matrices, their inverse is themselves, because you just need to swap rows again to undo them. And then remember for these types of elementary matrices, you just do the reciprocal along the diagonal to get the inverse, okay? So this would how you would express A as a product of elementary matrices. All right. Any questions about that? Okay. So there's just a little bit of time left, so I'll try to quickly end with the LU decomposition, all right? So the LU decomposition, it's factoring a matrix A into a product of two matrices L and U, where L is lower triangular with ones on the diagonal, and U is going to be upper triangular, although the diagonal entries are not necessarily ones though for U, okay? To find the LU decomposition, you want to reduce A to an upper triangular matrix. And here, this is kind of important. You're going to reduce A to an upper triangular matrix using only elimination type of operations, meaning you can't do any row swaps and you can't multiply a row by a non-zero number either, okay? That's going to give you the upper triangular matrix U, and then the multipliers that you used in your row operations will go into the matrix L, into these entries, okay? And one of the applications of the LU decomposition is using it to solve a system of equations, AX equals B. So the idea of this is if you have the equation AX equals B, and then we have A is equal to L times U, then we can like replace A with LU in this equation. and then u times x. If we replace u times x with another vector y, then what we can do is first consider the equation L y equals b, and we can solve for y in that equation using forward substitution, and we'll see how that works. After solving for y was equal to ux. So then to solve for x, you're just going to use that equation and solve for x using backward substitution, okay? So I'm going to illustrate that real quick with this example, and we'll end the review with this, all right? So what we want to do is we want to reduce A to an upper triangular matrix. So first we need to eliminate the 3 and the -4 using the 2 as a pivot, okay? So we're going to do row 2 minus 3 over 2 row 1 and row 4 plus 2 row 1. Sorry, row 3, which has a 4 in it. So yeah, row 3 plus 2 row 1, okay? And so that's going to give us 2, 0, 0 in the first column. And then let me see, row 2 minus 3 halves of row 1 is going to be 5 minus 3 is 2. -2 minus 0. And then row 3 plus 2 of row 1, so -3 plus 4 will be 1 here. And then 1 plus 0 is 1, okay. So then we have to do one more elimination. So we're going to do row 3 minus 1/2 of row 2. And that will leave us with 1 plus 1, which is 2. It's kind of interesting. It's all 2's. Okay. So then this is going to be the upper triangular matrix U in the LU decomposition. And then for the matrix L, it's really easy. So it's 1s on the diagonal, 0s on top because it's lower triangular. And then here, the multipliers that we used in the row operations are 3 halves. Here the multiplier is -2. So it looks like +2, but the multiplier is -2. And then here the multiplier is +1/2. And that's going to be L, okay? So it might look a little bit weird, but the way that I just kind of thought of it was, take the number in the middle and just change the sign and put it into L, okay? In your textbook, what's going on real quick is they always do subtraction. So for instance, in your textbook, they would say that this operation is actually row 3 minus -2 times row 1, and they would say -2 was the multiplier. That's kind of what's actually going on, okay? But just remember to kind of like take the number in the middle and change the sign. That's how I think of it. So then this is the LU decomposition. We have L here and we have U here. So if you multiply those two matrices together, it's going to give you the original matrix A, okay? Now for part B, which is trying to solve the system of equations using the LU factorization. So there's two parts to it. We're going to do Ly equals B and solve for Y. And then we're going to do Ux equals Y to solve for X, okay? All right, so let's look at B real quick. So as a matrix equation, this is equivalent to matrix A times vector x by z equals b being 2, minus 3, and minus 5. So there's two parts to this. The first thing we're going to do is solve Ly equals b using forward substitution. So L, I'm just going to copy down the lower triangular matrix that we found earlier. Times y, and so y is just like a sort of placeholder vector, so just do like y1, y2, y3 for y. And then we're going to set that equal to b, which from the right-hand side of our system, 2, minus 3, and minus 5. Okay, so the idea is if you convert this into a system of equations, now the first equation that you get is going to be 1y1 plus 0y2 plus 0y3 equals 2. Okay. The second row will give you 3 halves y1 plus 1 y2 equals negative 3. And then the third row gives you negative 2y1 plus 1 half y2 plus 1 y3 equals negative 5. So because L was lower triangular, we can solve this by doing forward substitution. So basically, we already know y1 equals 2. We're going to substitute forward into the next equation, and then we can solve for y2 now, okay? So this is going to give us y2 equals negative 6. And then we have y1, y2. We're going to continue substituting forward into the next equation. So y1 is 2. y2 is negative 6. And now we can solve for y3. That's negative 4 minus 3 plus y3 is negative 5. And that's going to give us y3 equals positive 2. Okay. Now that we solved for y, we still need to do u times x equals y. Okay. So then real quick, u, the upper triangular matrix that we found earlier. X is the vector of the original variables, x, y, z. And then y is what we just solved for. Whoa, okay. All right. So then just to finish this up, write it as a system of equations. And then do back substitution. And that will give you the solution, okay? So what is this last one? I think the x is 3. Okay. All right, so then that gives you the solution to the system of equations. If you want, you can try plugging in 3, negative 2, and 1 into here to confirm that it all works out, okay? But it is 6:30 now, so I'm going to go ahead and wrap things up with this. All right, no problem. I hope it was, useful, at least some of it, Let's see here. I would probably focus more on the exam questions because